Okay, well, welcome everyone to the second carbon webinar. So my name is Nigel Marks, and on behalf of the Australian Carbon Society and Curtin University, I'm delighted to be online again with my carbon colleagues around the world. So for those of you in Australia, good morning. And for those in the Americas, good afternoon and good evening. And for those of you elsewhere, in particular Europe, we apologise that you have to burn the midnight oil to be online with us. So before we begin, I'd like to remind you that we are recording this session. Not everyone will be able to watch this live, and so we'll be making recording available on YouTube afterwards. For those of you who missed our previous webinar, there's which was looking at the wonderful contributions of Professor Rodriguez-Reynoso. There's a fantastic YouTube video which I highly recommend to you, and you can find the link to that video on the Carbon Webinar website. So at the conclusion of today's presentation, we're going to have a question and answer session. We won't be having people speak out their questions. That's a bit complicated on Zoom. So instead, we're going to use the chat box in Zoom. Now, most of us are Zoom experts now, but just in case you're not, you can access the chat box via the icon, which is immediately to the right of the green share button. Please don't share any content. We just want chatting. So if you can type any comments that you have into the chat box, we'll collate those and we'll go through them at the end of the presentation. So you can type your comments into the chat box during the presentation or at the end, it's up to you. But if you think of a question when we're 10 minutes into the talk, just type it into the chat box and one of us here at Curtin will capture that and then your question will be addressed at the end. Okay, so with those basics out of the way, I'd like to introduce our speaker. So we're privileged today to have with us Professor Teresa Bandosz. So Professor Bandosz is full professor at the City College of New York and a well-known figure in the carbon science community. She has over 400 publications, 6 patents, and was selected as the Graphene Lecturer for 2016-17 by the American Carbon Society. Professor Bandosz has broad experience in the field of materials preparation and their applications to environmental problems relating to adsorbents for gas separation. So today she will be speaking on the topic, Beyond Adsorption, New Research Directions for Porous Carbons. Professor Bandosz, it's a delight to have you online this morning. So can you please now share your screen and commence your presentation?
So, yes, good morning in Australia, good afternoon, good evening to everyone. And first of all, I would like to thank the organizer for an invitation. I think it's a great idea because many of us right now, we really miss our carbon meetings. So that's, I feel like those meetings are really needed and very timely. So what I'm going to talk today, I'm going to give you the story how small pores of carbons largely affect beyond adsorption application. And I'm going to focus only on oxygen reduction because I have only 40 minutes, but also I'm going to mention some other application and of course, we also have some idea what they might be as CO2 reduction, the photocatalysis on carbon, or sensing, or of course, these supercapacitors. So how small pores largely affect the beyond adsorption application. What we really know about carbons we know a lot. They are old materials and some things are quite obvious. They are dirty, they are black, they have high surface area, and they are good as adsorbents. They are good to adsorb organics. We might have the problem with selectivity, and we can relatively easily modify the surface. For catalysis, the heteroatoms are important, and the pores are important for adsorption and surface area for dispersion of the catalyst, if we think about the catalysis. But there are also some aspects in the carbon science which are not so obvious. And it is that the pores with adsorbents, they can work as nanoreactors, and the pores and the strong adsorption potential can contribute to non-adsorption and also non-separation applications. So I cannot move the... So the hypothesis which I'm going to address today is that strong adsorption of oxygen in ultra micropores of carbons enhances the efficiency of oxygen reduction reaction. And in ultra micropores, I would like to be very specific here because we have in mind the pores which are similar to oxygen molecule. And if I would say that it was our hypothesis from the beginning, it wouldn't be entirely true, because at the beginning we really wanted to look beyond graphene, and knowing its exciting application, we wanted to apply the porous carbons for the application where graphene was very popular, because in fact it was found that the pores in the carbons, they are built of distorted graphene layers. But then we got the results, and we need to explain them, and it was not easy, and it is how, in fact, we formulated that hypothesis, and I hope that I'm going to convince you that they really might be important for these applications. So the oxygen reduction on carbons is a very popular topic, and a lot has been published on this. And there are really well-established fact that the heteroatoms on the surface, they are the catalytic centers, and also the defects are very important. And recently in 2018, it was stated by Yao and co-workers that any method that could alter the electronic environment of carbon atoms are also capable of enhancing the ORR performance. Well, it is true, but the porosity is not really affecting too much the electronic environment. Also, it has, of course, some effect, because those who work on carbons, we know that if we have more pores, of course, we have more defects. So the effect of microporosity, or the study of microporosity for oxygen reduction, could be considered as kind of a relatively old story. So in 1979, the paper were published where it was stated that in fact the pores, the micropores, they are not important for oxygen reduction. The authors, they studied many carbons, and of course at that carbons, they were really not modified with nitrogen. So they were the porous one and non-porous. And based on the dependence of the current on the surface area, they stated that the pores in the carbons of the high surface area are not really important. And they, in fact, had the reason to state it, because they give, it was because of the geometrical constraints. So if we assume that O2H minus ions, they enter the pores, they have to be solvated, and they are also the thicknesses of the layer and so on. So they should be 18 angstroms. So they should be larger than 18 angstroms in the diameter. So, but then of course, recently a lot of papers have been published on the ORR and doped carbons, and I just show you the few of them where if we have the high surface area carbons, we have a really high number of electron transfer on them. And there were also some specific statements about the effect of microporosity, and they were because the carbons which were studied had also micropores, or because they were even no heteroatoms on the surface. So the micropores were pointed out. However, the main stress was in mesopores because they are important for the transport of electrolyte to catalytic centers. So, but some results were a little bit deeper, like for instance, the group from the University of Porto, they studied the carbons, the porous carbons and non-porous carbon, modified with nitrogen and non-modified. And indeed, they found a linear dependence of the kinetic current on the BAT surface area. And what was interesting that there were two different slopes of that dependence for non-modified carbons and for modified carbons. And it looks like the effect for non-modified carbon was stronger. And recently they also found the dependence, the linear dependence of the current density on the surface area. And in this paper, for instance, it was also the authors, they use Zhang and I and all, they use quite interesting carbons with layered structure. And here is the distribution of the pore sizes. And they stated that rich micropores, they shorten the ion diffusion distance and decrease diffusion time for oxygen inside the pore channels. However, how they do it, it was really not stated in details. And quite recently, that very interesting paper was published by the group from Alicante, where modeling with experiment was combined, and to do it, the assumption, many assumptions were formulated, but the important is that the model assume, and for those assumption I refer you to this paper, that it was assumed that narrow and wide micropores are randomly distributed, and the oxygen can enter the pores equal. And what was found that in fact the reduction that we have two reactions, and they are seen on the LSV curve. So the two different, in fact, reactions. So in wide micropores, we have the oxygen reduction to the peroxide, and then in narrow micropores, we have the reduction of the peroxide to OH minus. It is quite interesting because it might explain the shape. I may go to the shape later, but it is, if we look at the calculation by Appleby and Marie, so those pores, narrow micropores, the question is what could be their size? And what I would like to mention once again to stress that we would like to, or we focus in our investigation on the pores which are really small, the pores where oxygen is adsorbed by strong adsorption forces, not really O2H minus ions. So how we started? Well, we started that we got those three interesting carbons. The porosity, so as you can see from A to C, the volumes of the ultra micropores increased, but the sizes were the same. The carbons had some content of oxygen, but we found that they were very hydrophobic. So simply it was not dissociated oxygen. And we know that if we think about oxygen adsorption, so oxygen likes the hydrophobic surfaces. So, and we look at the results and we found that indeed with the increase in the volume of those ultra micropores, with the onset potential was more positive, and also number of electron transfer increase with the increase in that volume. And of course, those carbons were very stable to methanol crossover and generally also more stable than PTC. But those are the general features of the metal-free carbon catalyst. So then we decided to study materials which were a little bit more complex. So we look at carbon forms where we had macropores and also mesopores and ultra micropores. But in this case, we modified them with graphite oxide to increase the oxygen on the surface, and then we reduce, and we also modified with sulfur and nitrogen. And what we found, well, here you can see the amount of sulfur and nitrogen which was on the surface, but we found that modification with heteroatom, in fact, we decreased the volume of ultra micropores, and for the carbons without heteroatoms, we had very similar volume of these ultra micropores. So I'm focusing on this, and of course, those two groups, they have no heteroatoms. So, and here are the results. Okay, so as you can see, the most positive onset potential for our sample was for those without sulfur or nitrogen, and also number of electron transfer was very high for the carbons. For this is the composites, reduced composites, and also, and it is the reduced foam or the initial sample. And also what is important to mention, and what we found also quite amazing, that on the porous carbons, usually on we have the number of electron transfer really close to 4, and of course the onset potential, it differs from then on PTC. The PTC is still the best one. So after this, we decided to look at ordered carbon. Of course, they have the mesopores, which should help with the reduction. And so we synthesize them from sucrose, then we oxidize the sample, we treat it with urea and heat it at a different temperature to introduce nitrogen. And here are the porosity results. So apparently we change the volume of ultra micropores, and of course the surface was also modified. And that volume of ultra micropores was very important for us. So we look in details at the distribution of the ultra micropores in this range. Why it was important? Because if we really think about the effect of oxygen adsorption and how that oxygen, how the bond, how it splits in the small pores. So there could be two factors which are important. So it would be the extensive factor, which we think is the size of the pores, and the other is the intensive intensive factor, which is the size of the pores, and the extensive, it is the volume of the pores. So and of course, right now I would like to keep in mind that I will go back to it. So is that extensive factor really important? Is the volume of the pores really important? But for carbons, it is really hard to distinguish, to determine that effect. So we thought that what would be important is, of course, the smallest, which carbon have the smallest sizes of the pores, and what is the spread of the distribution. So where is the maximum of the distribution in ultra micropores? So here you can see that ONC, which is the initial carbon without any nitrogen, it has the smallest pores, and then we have the carbon modified with urea. And of course, we did that modification to introduce nitrogen. We introduce a little bit, so it is seen here. And by changing the temperature, we also change the chemistry of nitrogen. Of course, we had the pyridinic groups, which were important, but in this case, in the case of this carbon, we have also the quaternary nitrogen on the surface. And here are the results again. So again, the best carbons from the viewpoints of the onset potential were those without nitrogen. And also, if you look at the number of electron transfers, so also the second after the PTC is the carbon modified with urea and heated at 950, but also the oxidized carbon. Also the slopes of the careful slopes were very good, so less than on PTC. But once again, it is really little difference between the carbon in the number of electron transfers. So we were trying, as I mentioned, intensive or extensive factor, but the question is how to account for them on carbons. So we look at the dependencies, and we plot the dependence of the number of electron transfer on the volume of the pores, which are smaller than 0.7 nanometers. So it would be that extensive factor, but also as an intensive factor, we have chosen the maximum of the peak of the distribution of the volumes in ultra micropores. And what we found here, that even that for the dependence on the volume of the pores, we could see that we had two different slopes. So one was for nitrogen modified carbon, and one was for non-modified carbon. So it could suggest that they are different mechanisms. And on the other hand, when we look for the dependence of N on that maximum of the peak, the good linear dependence was only for the carbons with nitrogen. So it looks like here the situation is more complex. And then since we studied those mesoporous carbons, where we know that the mesopores are important for the transport of the electrolyte with oxygen. So even if we assume that our ultra micropores are important, where we have that pseudo catalytic effect, so still the electrolyte with oxygen have to go there, and it would go there if the surface has certain number of groups which are hydrophilic. And the oxygen, it can in some cases it can bring this function, and so we look at the dependence of electrochemical surface area on the density of oxygen in those mesopores. And we found that, okay, we have the indication of the dependence for the carbons which are non-nitrogen modified, and for others we didn't find that dependence. So then we look at microporous carbons. So microporous carbons, and here it is an interesting story, because we in this case we modified carbon with as before, so we oxidized, but nitrogen was introduced from ammonia, and we were more successful with introduction of nitrogen. We had a little bit more, but what we found, that those carbons with nitrogen, the porosity was almost the same for all samples. So, but for carbons which were not modified, we had the differences in the surface area, in the volume of ultra micropores. So this was kind of a bummer for us, but then we were thinking, well, okay, if we have the same volume of the pores, so maybe it can give us some information, in a sense that we might see, or if we have, so we might see really no effect on the oxygen reduction. And here are the studies of the porosity, and for us this is, as I mentioned before, this is very important. So here you can see that those carbons modified with ammonia have almost the same porosity, and the carbons which were without nitrogen, they had much smaller pores, where it is only 0.1 nanometer, but at this scale where we are, it could be important. And so then, once again, the result, once again, the most positive onset potential was on the samples without nitrogen, and number of electron transfer too. So as you can see, the oxidized sample was very good, and the oxidized and reduced samples were found as the best. And then we were trying to base what we have learned before, and knowing how complex is all the problem, we were trying to find the relationship between the performance and the features of carbon, and the features of carbon which are really important for oxygen reduction. And there could be many features which are important for oxygen reduction. For some of them, it is really difficult to quantify the properties and to use it in any equations. But we were thinking that based on this, what we learned that number of dissociating group and electrochemical surface area should be important, and those groups they rather exist in larger pores, because if you think about very small pores, so the probability that the groups are incorporated to the graphene walls are really very small because of the geometrical constraints. And so we use this factor, which is important for the transport of the electrolyte, and also the volume of the pores smaller than 0.7 nanometers. And here is the dependence. So we look at the number of electron transfer, and we look at that PIF, and we found that for nitrogen-free carbons, we have really good relationship. And then we look at the kinetic current density and on volume of those micropores and on a volume of the pores smaller than 0.7 nanometer. And so it is a dependence for the small pores. And apparently I mentioned that we in the case of the carbons which were modified with nitrogen, so the distribution were the same. So we didn't see the effect, and the distribution of the points is likely related to different mechanism on those carbons. Then after all of this, so since very often it is considered that really microporous carbons, they are not good for many processes because of the kinetic limitations for access of the molecules for the pores, we decided to look at carbon molecular sieves. So carbon molecular sieves, so we obtained two sieves from millipores. So it was the carboxane and carbosieve. And we modify those carbons, we oxidize them in air and in acid. Here you can see the distributions from nitrogen. So even looking at those distributions, you see that it looks like that carboxane is more stable than carbosieve, where when we oxidize with air, really not too much happened, but oxidation with acid definitely decreased the volume of the pores. Also, the sizes are similar than before. And since for us that oxygen adsorption is important, and the interaction of oxygen with the small pores, we decided to measure also adsorption of oxygen on those carbons. And recently, and so that analysis was done by Jacek Jagiello, and we compared the distribution from oxygen and nitrogen. And in this work, in fact, it was presented that if there are no specific interactions, so the distribution, they should be similar. So the similar distributions were expected, but not exactly the same distributions were obtained. So here you can see for initial sieves, for carboxyl and red lines, they represent the distribution from oxygen. And so especially for sieve, which was modified with acid. So even though the sizes, they might be considered as in similar range, we have some more heterogeneity. So that heterogeneity, so of course, what is the origin of that heterogeneity? We thought that it might be due to some interactions of oxygen, some might be affinity of oxygen to certain oxygen groups on the surface, because do not forget that we oxidize that carbon with acid, and we significantly decrease the porosity compared to the initial sample. So if we look at the comparison of the porosity calculated from nitrogen and oxygen, there are mainly mainly similarity in the results, and you can see this, for instance, for volume of micropores or volume of ultra micropores. However, some differences were observed for specific volume of the pores, as I mentioned, and you can see it, especially for that acid, where we have really much higher volume of micropores and ultra micropores from oxygen adsorption. Of course, the question is if it is really a volume or just related to more oxygen interacting with the surface. So here are the results of the electrochemical test, and it is interesting because Cx you can see as dotted line and Cs as the solid line. So what happened after modification, especially of Cs? So we increase the kinetic current, and those two sieves, they have different shapes of the LSV curve. And if we look at the number of electron transfer, you can see that the best and very close to PTC is Cx. And then two others are Cs and Cs oxidized. So the carboxyl, which has the high volume of the pores, it's not really here. But when we look at them at the onset potential, so the carboxyl was not really very good. It was the worst one from the other, and all others, they have the similar values. So of course, the question is why, and it was why, and maybe it is still why. Okay, how to explain this? So we know that working on carbon and understanding what's going on is not very easy, because we do not have the method which could give us the detailed information about what is really on the surface. So even if we look at chemistry, we have to look at the combination of different methods, and sometimes more methods we have, so more questions are asked. Okay, so and it brings us the complexity to the problem. So in this case, we studied the chemistry since we noticed that effect of oxygen. So we studied the chemistry using the titration experiments, where we could get the information about the dissociating groups. We studied and we did also the thermal analysis. So here are DT curves, so we could see what was the weight loss and what was really removed on the surface. And here is what we got. Okay, so what was interesting with carboxane, that it was the only one basic carbons. Okay, so completely different from others. It really didn't have the acidic groups on the strongly acidic groups on the surface. And so that basicity was quite puzzling. And if we look at the differences in the all dissociating groups in our experimental window, they are really not so big. And if we look at the decomposition of the weight loss at the decomposition of the oxygen group, so that carboxane is very stable, really very stable, and the groups, they decompose later. So if you look at the peaks for other carbons and carboxanes, so, and you look at this data, so you see that, well, it is some discrepancy in this. So that carbon, that carboxane, was interesting, and that gave us an idea that likely this carbon is very rich in electrons on the surface. So we did XPS, and as I mentioned, XPS is a great technique, but sometimes it brings more questions than answers. And so we look at as oxygen. So obviously, when we oxidize that CS with acid, we slightly decrease the oxygen on the surface. But what happened? We increase the number of CO bonds. And if we look at the surface, so if we look at the surface area of this carbon, it was really much less than this one, and this carbon was behaving surprisingly well. So we should have the high density of those groups on the surface, and we, in fact, based on the analysis or all of the combined analysis, we assign them to ethers on the surface. We know that they are hydrophobic. And it was also that interesting paper by Chen et al., where in fact they also found that oxygen groups are important for the sites for oxygen reduction. So it was really not indicated how, but it was indicated that they really have the crucial role in this process. So the question is, what is the crucial role? So this is our first scenario, what we think happens in ultra micropores. And once again, we think about the pores, which are small in size, similar in size to oxygen molecule. So oxygen molecules are in water, then those pores are hydrophobic, so they withdraw oxygen from electrolyte. And since water is very close, we have the strong adsorption potential, we have the splitting of the bonds, we have formation of OH, and that OH, it doesn't like to be in these pores, it prefers to go to water. So the site is open for another oxygen reduction in the pseudo-catalytic process. But with the new results, we thought that, okay, the pores are important, but also and as we found also before, the hydrophobicity is important, but not only the hydrophobicity in the pores, but also the hydrophobicity of certain groups on the surface, because we might have the oxygen groups which are hydrophobic ethers, for instance, and we have, so what happened? We have oxygen in the electrolyte, and those groups, they attract oxygen. So not only the pores, but also the groups, they attract oxygen. And then we have the reduction in the pores, and the oxygen is ready so to enter again. So it is some kind of concentration at the pore entrance. It is, of course, it's our hypothesis. But here, this might also somehow help to visualize the question what I have, if it is intensive or extensive effect. So because you see, that oxygen has to be close to water. So really the volume in the pores is not so important. What is important, what might be important, is the number of those very small pores. And here it may also bring us to the effect of the defects, where we have, if we have the defects that they cause kind of valley in the graphene layer, so maybe this effect is similar. Then we did inelastic neutron scattering, because we wanted to see if the carbons are really able to give us those OH groups even without any potential. And we did it in a Oak Ridge lab, and we exposed the carbons to oxygen, and we subtracted the spectra from the initial carbon. And as you can see, it was no effect after adsorption of oxygen. But after adsorption of oxygen and water, we definitely seen the peak from OH group on the surface. So we had the formation of OH, we have the reduction of oxygen. And what I would like to mention, which might be also something for a future study, and maybe to whet your appetite a little bit, we didn't study this, but I think it would be important really to understand what's going on, why the shape of LSV curves are so different. In some carbons we have this, in some other we have, and after modification, for instance, we change the shape of the curves, and on the PT carbon it is always like that. So that's so it could be related, of course, to the differences of the processes, but maybe such curve is related to different sites and, of course, the complexity. So the important features on the surface of carbons, of course, there are many, and as I mentioned, some of them we are not able really to quantify well, but we think that oxygen adsorption is important, and the challenge is in the surface, because we have the pores and we have the chemistry. So how to combine it? It is not easy, because we are not able, even though we are able to have the carbon, the graphene with chemistry, we are not able to have the carbon, the pores in carbon without oxygen. Maybe of course, the calculation would help in this case. So what is my message at the end? We think that adjustment of the porosity and those small pores is important, can help with ORR efficiently. And if we combine the N and S, for instance, or boron doping in larger pores and the porosity, we can get really good catalyst. And we think that the effect of micropores, it does not equal to the effects of defects. And so oxygen adsorption matters. Also, it is the talk about beyond adsorption. Adsorption matters, and adsorption matters in many processes, and sometimes it is just really, it is no focus on this because but it might help. And here we think that the sizes of the pores matters. Of course, beyond adsorption are also these applications, but we think about more energy related applications. This application, they can make maybe someone rich. And this is the paper which we published recently about beyond adsorption application. It was based on the discussion at the carbon workshop in New York City after last carbon conference. And this is the paper where I addressed that silent aspect of carbon nanopores. So where you can see also some other application and going more into details. And here are the sponsor and the contribution of this for this work from CCNY, from Argentina, Spain, France, Rutgers, Microporosity and Oak Ridge. And here are the 4 contributors from my group, which are on this group pictures, and those who are not on this group picture. So that's all. Thank you very much, and I hope that that I make you more curious. And we have the hypothesis, we have some indication that it might work, but of course much more work is needed in this field. So thank you very much for your attention.
Well, thank you very much, Professor Bandosz. That was wonderful. Lots of food for thought. Just speaking for myself, I do most of my carbon work on a computer, so I find myself trying to imagine how you would even construct such wonderful structures to produce these effects. We're now going to try and do a Q&A session over Zoom. So if you use the chat box in Zoom, you can type your questions in and I will read them out and then pause for a moment and give Teresa a chance to respond. Yeah, so let's go through our first question. So how close is carbon or doped carbon to replacing platinum on carbon?
Oh, it's a good question. How close in which aspect? Because if you look at the number of electron transfer, we are really close. We are almost the same. If we look at some current density, we are also very close. We are still far away. However, some papers were published that the carbons can have the onset potential even better than PTC. I'm not sure, but replace is also in the terms of money, okay, and the terms of the cost. So I think that we might be close, but how close, I really don't know.
So let's just go to the next question. So it appears that we desire 2 competing things from our structures, ultra micropores to pseudo-catalyze the reaction, and in contrast, mesopores so that the O2 can reach the pseudo-catalytic sites. Is there a synthesis strategy that we can employ to create such structures?
Experimentally, yes, because we can get, for instance, if we do the template carbonization, we can get mesopores, and also we can get ultra micropores. But the problem which I really do not know how to address is that volume and the size of the pores, because I think that for this it is important that we have the small cavities in the carbons, which could be active for that pseudo catalytic activity related to oxygen adsorption. But I think that there are the strategies. We can also do the template carbonization using the precursor, which has sulfur, nitrogen, and others. So it is doable, but of course, as I mentioned at the beginning, the problem is to control of all of this and to describe all of this.
Okay, so in the samples with urea, nitrogen get introduced into the carbon network, and have you done the heating at different temperatures? And if so, does that affect the level of doping and their properties?
Yes, we did, and as you can see, we heated them at 3 different temperatures, and we slightly affect the nitrogen content. So basically, I think it is the same, but we affected the distribution, especially in the case of this carbon. So we noticed the differences. We have the quaternary nitrogen, we have the pyridine and oxide. And if I go back, so, and the performance, okay, so here, so we introduce nitrogen, onset potential was worse, and in the case of the number of electron transfer, only the sample which was heated at 950 was really good, and it is this sample. And then it was, of course, the sample at 600. So we the problem with number of electron transfer, as I mentioned, that in some cases the results are really close to 4, okay, for all carbons which have micropores.
So what is the next advance that you see in experimentally understanding the porosity of carbons? That's a nice general question to finish with.
In experimentally understanding the porosity of carbon, what we see, it depends on the molecule which we use as a probe, okay? So of course, to see best, so we should use the smallest molecule as possible. I think helium would be too expensive. However, such efforts were done before, and I think the effort, of course, has been done to combine to combine different molecules of different sizes and to have the distribution, the range of the distribution. But we have to be really careful with choosing the probe, because, for instance, CO2 is considered as a good probe, but they were the papers, and we also found that it could interact with the carbons, with the specific groups on the surface. So in understanding the porosity, we have to understand the molecule which we use as the probes, and also how the surface can interact with them.
Okay, well, we're almost bang on time now, so that's fantastic. So with that being our final question, I'd just like to thank you again, Professor Bandosz, for a wonderful presentation. It's given me a lot of food for thought, and I really appreciate you putting everything together for this presentation tonight. So before we finish, just a quick reminder that our next carbon webinar will be held in just under 2 weeks. It'll be on a different day and at a different time. So we're trying to accommodate all the people at different places around the world. Our speaker will be Professor Rod Ruoff, who is very well known to many of us. And he's going to be speaking about graphene, multi-layer films, F-diamine, and more. So he'll be giving us a fantastic overview of the work that's done at his lab in Korea. So I look forward to seeing you all online. In the next webinar, we may try a different technology to talk to each other afterwards. There's a piece of software called GatherTown which if you're keen, we'll have a bit of a play with together, and we can have a bit of a private talk as well as a collective talk. But that's all for next time. So I look forward to seeing you then in just under 2 weeks. So thanks for joining us, and good afternoon, good morning, and good night.